Okay, first of all, I'd like to welcome everyone to the Climate Resilience Network talk. It's going to be by Karen Prestegaard. Karen is, I guess she's been at the University of Maryland for a little over 35 years. She's really highly valued in our department for the various roles that she has taken, and I'll get into those a little bit in a little bit. She's also a critical part of the Grand Challenges project that involves ESSEC, AOSC, geography, and geology. Her expertise is in the area of hydrogeology, I guess hydrobiogeochemistry, geomorphology. She works on a whole variety of different topics, ranging from rivers to carbon storage, some things on nitrogen, with wetlands and in the area, and also up into Canada and worldwide. She's someone who does an outsized part or contribution to our education and our teaching and mentorship in our department, and is someone who's really appreciated for that. And then scientifically, she's just enjoyable to talk to. She's interesting, she's a clear thinker, and has some really good ideas that are fun to talk about. Today, she's going to talk about some of her work with at the intersection of climate, precipitation, I guess droughts, and floods, which is part of the work that she's doing with respect to the Grand Challenges project. So I'd like to thank her and welcome her.
Thank you, James. And again, thank you for everybody both here in person, so I have people to talk to, and online. I really appreciate it. So what I'm going to talk about today is what we see in terms of the changes in precipitation, how the stream channels are responding to that in terms of droughts and low flow conditions, and thinking about how we're interacting with those events, particularly with regard to flooding hazards. And anybody that's been driving around during some recent flood events, I was driving around on July 19th, that major summer flood this summer, and it was pretty scary because we didn't actually have much warning. The warning was actually in a different place than the event happened. And so we didn't know whether to drive through sort of lowland areas or not. But anyway, I'll be talking about flooding hazards and their relationship to both the storm events and the landscape that falls on. I'll be looking at erosion hazards, and this looks really severe, but I'll show you something that looks kind of like this as well. This is an old village in Germany with some really recent flooding that has caused severe erosion, and also about droughts, which is our water resources, which are as important as floods and are responding as well to changes in precipitation timing. So one of the things that we've been looking at is that we see across a lot of parts of eastern United States increases in the intensity of storm events, but only a minor increase in the annual precipitation. So if we're getting bigger storms and not much more annual precipitation, that means there've got to be more times with smaller storms or more times with gaps between storms. So this is what some people call, the climate whiplash. We're getting bigger big events and smaller low flow events. So we would like to tie these to what is happening in terms of changes in the patterns of precipitation, and then also identify how the landscape is responding in particular to the storm events, and also what parts of the landscape respond differently than others. And finally, I won't talk much about this, but we need to think about how we're going to use this information. Do we use it for hazard mitigation? Do we use it to increase how we do land use planning? Do we put up warning systems on places we identify as being ones that are going to respond more violently to the storm events? And just for fun, here's the thunderstorm watch area for the the July 19th storm event. Here's Washington up here, and the major part of the storm is about where it says severe thunderstorm watch on that. So that just points out how hard it is to pinpoint where these severe storms are actually going to happen. Where it's going to happen is also in Maryland, because that's what we're focused on here. And Maryland is on the eastern part of the United States, which you know. There are, I wonder if we should make the room a wee bit darker. I don't know. Is there a way to do that? Let me just randomly hit one of these buttons. Nope. What did I just do? Oh. That wasn't the right button. All right, stop that. What did it do?
It's opening the shades.
Oh, that's the opposite of what I wanted. Well, I'm not going to try to do anything else. I'll let somebody else look at the lights. All right, so these basins along the east coast of the United States, they start at the Appalachians, more or less, and thank you so much. And then they head towards the coast. So they're all running parallel to one another, but they're not all the same. The ones further to the north are places where the glaciers once were, squishing down on the crust, and then the mantle kind of oozed away to the south, which is where Maryland is, right? We're in the oozing part. And that means this area uplifted a little bit during the Pleistocene, 20,000 and more years ago. And then the glaciers melted, and then the mantle oozes back again. But as a result of things being squished down to the north and then coming back up again, as that snow, that runoff came off of those watersheds to the north, it started some deeply incising some of these existing stream systems, such as the Susquehanna, the Connecticut, and some of these other streams. So they have relatively narrow valleys. Further to the south, the smaller streams like the James, the Roanoke, the Neuse, are heading from the Appalachians and are going down to the south, but they have a fair bit of the coastal plain in them. The coastal plain runs along here. And when we get up to the Potomac River, it comes down to the tidal section of the Potomac estuary. There's really no coastal plain section of the Potomac River, right? And so therefore, all these other rivers are coming down, and then as they're getting further downstream, they get wider and wider and wider, right? So what happens then is they're going to attenuate some of the floods as the floods spread out onto the floodplain. Just trying to get a general picture in your head. So this is just a flood frequency curve. So when people say it's a 100-year flood, that means on an annual maximum series that has a 1 in 100 chance of a probability of occurring any given year. The 1.5-year flood or 2-year flood, that's about the range of the floods that build and maintain stream channels. Not big floods, little floods build stream channels. That means little floods are going to be the ones that change stream channels or erode stream channels. All right, so the point that I made about what the width of the floodplain is and how that matters is that as we go from upstream to downstream, the flood flows can stay about constant, proportional to basin area, or they can attenuate, and therefore this exponent here in the power function relationship between the peak discharge and the basin area would decrease, and I don't ever see ones that increase. We'll ignore that here. So we're going to mainly see a range of behaviors between these two. So if we look at all of these basins along the East Coast here, if we go look at the Delaware, the Susquehanna, Connecticut, they all have 100-year floods that attenuate with an exponent of about 0.87 or something, whereas the Potomac, in this kind of color blue here, is way down here, and it's sitting between the ones further south on the coastal plain that have more attenuation because they go under those big wide floodplains, but also their bankful floods are like 8 and 9 times, their peak floods, 100-year flood or 200-year floods are 8 or 9 times, 6, 7, or 8 or 9 times the bankful flood. In other words, the floods are bigger. They're getting more hurricanes and tropical storms. The ones to the north, biggest floods are snowmelt floods. You just don't melt snow all at once the way a big storm event comes in all at once. So basically, that's what that's about. So one of these things is climatically controlled, which is how big is the flood going to be, and the other is geomorphically controlled. Okay. Now that we think we understand that, I'm going to come in and say, yeah, but that's not true of where we actually live in Maryland. So here's the Potomac River. It's the boundary between Maryland and Virginia. We own the river, us folks in Maryland. And during the most severe droughts, Virginia always begs to get more of the river. And they, the last major drought, they put the intake further out into the river so they wouldn't have to drink sludge, basically, which I think is a good thing. You see a couple of things on this diagram. You see the fall line. The fall line is this sharp boundary. It's not exactly the Piedmont, the coastal plain boundary, but it's pretty close. It's where the waterfalls are. And that's where the water energy was back when they first built all the cities along the fall line, because they didn't have coal, gas, or oil. They were using water power. So DC, Baltimore, up here to Philadelphia, we're all located along the fall line, as is Richmond to the south, and all the way on down. You see that there are parts of the coastal plain here, but they're their own little systems. You also see all these little tributaries coming down here, coming from those little mountains coming down, and then they also go towards the Potomac, because the lower part of the Potomac is greatly in size once you're downstream of Great Falls, right? So that incision meant that all of those rivers changed direction and started flowing towards that, making all these short little segments of rivers that are flowing over and into and cutting into bedrock. All right, let's blow that up just to see it better. So you can see all those little tributaries coming down. They're crossing the Piedmont coastal plain boundary. So here's Ellicott City that you probably know about because it has severe floods. One of the reasons for the severe floods is they put it just as the river comes into this gorge, right? So everything's being funneled into one narrow place. That's, again, geomorphically controlled. Here's the gorge there. Here's the gorge on the Anacostia. That's the northwest branch of the Anacostia, which is a really nice place to go hiking because it's a pretty gorge, and there aren't many river crossings because they don't put roadways up and down into those gorges. So these rivers have a different morphology than what I just explained. One of the things is that the upper parts of these rivers is where the floodplains are wide. Where there is no floodplain at all is these narrow gorge parts just before you get to the coastal plain, and then they open wide up again when they reach the coastal plain because that stuff is so easy to be eroded. All right. So our question is, in then all these places where people live, where they put all these road crossings, how does that morphology interact with the big storm events that are going to hit this area? Okay, so now we're going to talk about the relationship between the size of the storm event and the size of a watershed. So this is a time and space scale of atmospheric motion. It's what we kind of put up to say, yeah, if we look at thunderstorms, they last a fairly short period of time, minutes to hours, and tropical storms and hurricanes last much longer. They also are spatially more extensive. And you've seen that every time you've looked at a satellite image of one of these big, massive hurricanes this past year come trundling across the Atlantic. If it came over the East Coast here, it would cover a huge area. That's exactly what Hurricane Agnes did back in 1972 and what some of these other big hurricanes did. They covered big spatial areas. They rained for 24 hours. There's bands of rain in those tropical storms that are intense rainstorms as well. A thunderstorm, on the other hand, a lot of ours go up to the northeast, northwest. They're heading northeast, and so they're moving along like this. They don't cover big spatial areas. With their orientation, they might cut across watersheds that are even fairly small, but they're only going to cover the entire area of small watersheds, not big ones. Okay, well, the next part of that, why that's important, is that there's an inverse relationship between the intensity of a storm event, this is in weird units, meters per second, not centimeters per hour or something like that, and the duration is in seconds. But just to clue you in, here's a 1 minute duration, 1 hour, 1 day, 1 month, 1 year. This is the biggest precipitation events ever measured on the planet. That doesn't mean they're the biggest ones on the planet, it means biggest ones ever measured, because we don't have gauges everywhere. So you see this inverse log function again between, or power function again, between the size, the intensity of a storm event, inches per hour, centimeters per hour, meters per second, and its duration. All right, so I just told you, oh, and by the way, some of the most intense short duration storms are actually measured in Eastern United States, globally. So we get some of the big winners here. And we think we just measured some other 5-minute ones between here and Baltimore that exceeded that just in the last year. Okay, so if we look at small watersheds, they are going to respond to short duration thunderstorms because a thunderstorm can cover the entire basin. So we can get a 2-hour storm that can create a big flood, in this case, a 12 square mile watershed. They'll also be hit by the intense waves of bands of precipitation that come with tropical storms and hurricanes. So when we look at the flood frequency curve, let's say for a small catchment, we often see this bimodal distribution here, where there's one relationship for the recurrence intervals under 10 years, and then all the ones up here were tropical storms or hurricanes, or almost became tropical storms and ran into a frontal system. I've taken this flood frequency curve and turned it kind of on its side, not as on its side, but essentially I've plotted a recurrence interval on the y-axis, and time is along the x-axis. And one of my students, Alex, hates it when I do this, but I'm doing this just to show you that the biggest event in the record that's over 70 years long, in this case, was 2006. It was a tropical storm hurricane, but there was a cluster of other tropical storms and hurricanes back in the mid-60s to the 70s, and we're seeing a recent increase in floods now caused by these intense storms. So those two distinct mechanisms in the time series are happening at two different parts of the time series. This is what's happening more recently, are these intense storms, and in the past we had this period with tropical storms and hurricanes that really hammered this particular region. Now, how do we interpret that? Well, I would look at that and say, that's a time series that tell us both those things can happen, right? Can we predict in the future whether we're going to get a tropical storm or a hurricane in this basin next year? Not very well. I could be pretty assured that we're going to get more intense short duration storms because that dominates the record, and the fact that they're recently increasing intensity suggests that they might continue to increase intensity. Okay, how do the basins respond in terms of the flooding associated with these storm events? So here I've just taken two basins. One is a 21 square mile basin with about 20% impervious cover. That's close to the average for this region. And one's a 1 square mile watershed with 18% impervious cover. So the impervious cover is the same. One's much smaller than the other. And they're both viewed as small by USGS standards. Okay, so here's 1972 in Hurricane Agnes. You can see the kind of trend towards increasing floods in the blue line, the bigger one. That actually has nothing to do with climate. If we compare that to forested catchments, essentially that's a urbanization trend, right, which we could take out, but it's nowhere as big as the climatic forcing, which is bouncing around these other floods. Here's in red is that small basin, and you see one of the problems with small basins is that we usually don't have records that go back 80 years for those. It's just recently that people said, we better measure these things because they're starting to explode in terms of their importance for flash flooding. And that's why we see in the last decade or so an increase in monitoring of those. And if we just want to compare, we've got small urban, small forested, large urban, large agricultural. We don't have entirely forested watersheds that are large. And you can again see the urban basins win, whether they're small, they're even bigger back in the 70s than the ones that were bigger. And you also see that even the forested small watersheds have fairly significant floods in this recent time period, right? So that's the climate forcing that we're seeing there. Okay. I hope that you get the message that these small catchments can really respond dramatically to storms, that we don't have very many gauges on them. We gauged some of the ones, this record here from the mid 60s to 70s is because they installed for a 10-year period gauges in the upper part of Northwest Branch with the intention of monitoring the effects of urbanization. And they put them in and caught this time period of hurricanes. And that's really what they measured. You know, that overwhelmed the effect of urbanization. It was exacerbated by urbanization, but we actually have reinstalled gauges there so we can actually interpret them better nowadays. We'll give you more of the details on that later. So we've reinstalled gauges in all those upper watersheds. We've installed gauges on small tributary streams that come directly into Northwest Branch, and I'll tell you why in a minute. And then we've got USGS, and we've got some other of our own gauges in the rest of this network, again on small streams, but most of these are bigger than like 6 square miles. The reason we picked Northwest Branch was because it had those geomorphic elements nicely arrayed, the upper part of the watershed with those wider valleys, a nick point, which is this essentially waterfall midway down, like Great Falls, it's just a tiny one. And it has a sort of upper incised valley and a lower incised valley, and then it pops out onto the coastal plain. So you see the change in valley morphology as you go down and river morphology. That also influenced where people live. So you can see here just an overview as though you're kind of flying over burnt mills and looking down on the landscape. This is why it's a nice place to hike up and down the stream, because no one is trying to build near the stream because it's too steep. And the depth to bedrock is really shallow, so it's really difficult to put a road across there. You have to put bridges, et cetera. So it's expensive. So the number of roads across Northwest Branch are, there's this one here, and then you have to go all the way up to Randolph Road, and then you have to go all the way up to 200. So there's not that many road crossings because of the character of these valleys. The other thing that you see is below the nick point, the valleys are even steeper because this nick point is there. There's the dam. And the tops of the hills are pretty much covered with the suburban development because it's a flat top of a hill. And that has consequences as well. All right, so here's the tributaries that go into the main channel of Northwest Branch. There's the tributaries that come in up here, and they were there before the stream migrated headward. This all happened in the Pleistocene, by the way, as sea level would rise and fall and the mantle would ooze down under and retreat back again. We had the progression of nick points up these valleys and incising the lower parts of these stream systems. Okay, so here's the tributaries, which are steep, but they have kind of concave up profiles above the nick point, and they're convex profiles below. And that convexity coincides with bedrock outcropping in the stream. All right, I'm just blown that up a little bit here to show you that. And we can measure that. We've got nice metrics to enable us to say, oh yeah, the streams below the nick point have an order of magnitude higher steepness index than the ones above it, something we can quantify quite easily. We also did seismic refraction profiles across these hill slopes down into the valleys, and we did this up and down the stream and saw pretty much the same configuration everywhere, which is the tops of the hills have the greatest depth to bedrock. And as we get further upstream, it gets even deeper. Along the edges of the stream before you get to the channel, you're pretty much in the bedrock. So these blue colors here are the bedrock, and the soil is the brown cover overlying it. And this is determined from the velocity. So the higher velocities because the rock is more solid, lower velocities because it's going through porous soils. And there's Mong Hong and John Harris out with us collecting data about a year ago. Okay, so how do these streams respond to storm events? So this is about a 2-year flood. Remember, that's that low recurrence interval flood that builds and maintains the channels. So we see that if the channels aren't urbanized, they fall along this green line, as do the channels above the nick point. They're like, yeah, we're urbanized, but we can deal with that because we have these low steepness indices. We've got more depth to bedrock up there. But if they're concave channels below the nick point, they rapidly respond to this increased urbanization. You get almost an order of magnitude increase in that bankful discharge, right? So what does that mean? That means all the places with these short, steep tributaries that are cutting from these upland areas across these incised zones into the channel. And here I'm not showing Northwest Branch, I'm showing the Potomac River. So all of these steep tributaries that come essentially into the gorge section of the Potomac River are just downstream of that. And to point that out a little bit more, this is where we have some of our really big roadways. So I told you I was driving across the DC area during that storm because I listened to the weather report and said, well, that's not going to miss us. I'll just get in my car and drive. Yeah. Anyway, I was trying to get to see friends at Great Falls, and I drove here along the Clara Barton Parkway. I think I drove along here and then into here. Look at these parallel roads that cross all of these short, steep rivers, those ones that are in urbanized watersheds and just really respond dramatically to flood events. And so if I was going to say, most of these are not gauge streams, by the way, and flooding was creating havoc in this whole area. So we know that these are going to respond dramatically to the floods. We don't have really good ways of telling people, stay off this particular part of the roadway. We're not shutting it down in advance, et cetera. One thing is people don't put up with roads being closed when nothing actually happens. So something to think about. This is the storm of July 19th. It's kind of a weird storm. It almost went east-west. It was just following my route as far as I could tell. And you can see this is where the intensity of the storms were. This is this area of short, steep streams, almost right in the same place there. Okay, so how did the streams respond? Well, one thing is they rose really quickly. And here's Sligo Creek and Tacoma Park. It's a couple of feet above flood stage, and it got there within 2 hours of the initial rise. So it just was rising at 102 centimeters per hour. It's rising at a meter per hour. This is this little 1 square mile watershed, almost as much impervious cover. It's much smaller, so it has less water going into it, but it's still rising at about 67 centimeters per hour. Again, pretty fast rise. And that actually wasn't in an area that flooded roadways, but Sligo Creek was, and some people that live in Tacoma Park experienced that flooding. This is now normalized to this precipitation, which is varying over the region, and you can see that we would expect the bigger watersheds to have longer rise times. And for the most part, they don't really until you get to watersheds bigger than about 10 square kilometers. And then we see that, but part of that is just because we're normalizing it. And we have these different amounts of precipitation occurring as well. The next question we asked is, okay, so we get these flashy storms, that's a hazard. We should tell people, don't drive here, or we should tell people in advance which of these streams are going to be very flashy, or maybe put monitoring devices on some of them. The other thing that we worry about is how much erosion is happening and whether that itself is going to take out a roadway or fill up a culvert with gravel and all the other dire consequences that can happen. So we've been monitoring, we go out and measure the geomorphology of these channels, their width, their depth, we gauge them, we measure what's on the substrate, and we figure out when these particles can move. If lots of these particles move, that can move downstream and get stuck somewhere. So sometimes they fill up under bridges and culverts. So lots of stuff moving often isn't a good thing. So the metric we just used was how many times does the stream get above the threshold of motion, right? So that's something we did just for last summer. And you can see some of the smallest streams were exceeding the threshold of motion up to 40 times during one summer period. In other words, every little storm event would set them off. Now, that's not because they got hit by all the really biggest storm events. It's because they had fairly small stuff in them, right? So they didn't have big enough stuff on the stream bed to really protect the stream bed, so it just kept being eroded. The fact that they're small is part of the issue here, because these streams migrate headward, like the whole Anacostia did. They'll migrate headward when land use changes and what used to be a stream channel, where the stream channel began, that will actually change place and it'll move further up the watershed if more water is coming in. So it's an adjustable parameter. The stream isn't always in the same place. If you give it more runoff, it kind of moves upstream, but it's moving upstream through what used to just be soil mantled hill slope. So it's not cutting through stream gravels, it's cutting through soil. And it's bringing in all this fine sand and stuff. And so these small streams now are probably flowing over mainly sand, and they're just moving all the time, all right? And it's sizing downward, et cetera. So this probably tells us these streams have run out of coarse sediment, or they've migrated headward away from where the coarse sediment actually begins. But the ones that have coarse sediment, for the most part, are close to being threshold streams or eroded all the way down to bedrock, in which case they're not eroding much more anyway. They're already eroded to bedrock, so they're not going to supply debris for downstream, but they're pretty incised. But older communities, particularly in the coastal plain, are kind of at risk here. So this is a city of just a little part of the city of Greenbelt. You can see the roadways here and all the homes along the road, and then this massive gully going right up to the roads, okay? And the concern here is this is what that stream looks like. There's this giant chasm. They call it the Grand Canyon of Greenbelt. And it's formed by essentially these streams that were propagating headward. You can see it's cut into soil. You don't see stream gravels or anything. There's a break and slope. This is where the stream channel probably began before agricultural erosion. And then when they converted that landscape from ag to urban, they said, oh, here's where the stream channel begins. And that was actually where a gully formed by agricultural erosion started, and they should never have put the storm sewer outfalls there. And that anchored in place an erosive gully, which is now threatening to undermine essentially the roadways. Now, we decided that it was fairly stable. We monitored it for a couple of years, and then this past year, I was blown away by the magnitude of the storm events that hit this area, okay? So this past year, the average precipitation was maybe 1.4 inches per hour, but we were seeing storms with durations of 5, 10, 15, and 30 minutes exceed by far the 100-year precipitation events in the NOAA Atlas 14. They were really big storm events, short duration. But it doesn't take a big duration storm event to get runoff from flowing down the street or from these lawns with very thin soils over clay bedrock or clay material to these little points of red here, which are the storm sewer systems. There's a very short distance that runoff has to go to get to that stream head. So this is where the design of an older community worked for a long period of time, but this shift in intensity of the storm events has put them at risk of possibly reactivating that head cut. So we're all sort of looking at this tree saying, please stay there, because it's currently keeping that whole gully erosion in check. All right, so I'm gonna end up with a short discussion of the other side of things, which is not the storm events and how they're interacting with the landscape, but the low flow events. So we have a couple of different ways that we look at this. One is we look at the probability distribution of all the discharges in a year. We call this the flow duration curve, or you can think of it as a daily discharge probability. And so we express that as the percent of time that the runoff is equaled or exceeded. Runoff just means you take the discharge, divide it by the basin area, and turn it into something like millimeters per day instead of cubic feet per second. All right, so you divided by area. And you can see that up here are the big flows. They range over an order of magnitude. And then a lot of the time, particularly for these black ones here, which are the forested watersheds that are relatively big, these, not relatively big, they're 3 and 0.3 square kilometers, so they're small streams again. But you see they maintain their stream flow, even though these other ones are just not. And then we see for the ones that are urbanized, but they're above that nick point, have more depth to bedrock, they maintain the stream flow pretty well also, but they plummet a little bit at the end. But the ones that are downstream of that nick point that I talked to you about before and has a shallow depth to bedrock, they're kind of cut into the bedrock, they have higher storm flows, but they essentially just start draining out and they lose their stream flow. So this is a geomorphic control on what the flow is in these tiny little streams. So there's the question that you're probably begging to ask, why do we care about the low flow that happens in tiny little streams? Don't we get our water resources from bigger streams, right? But where do the bigger streams get their water, right? Some of it comes in from the small streams and moves downstream. Some of it is more locally derived from groundwater coming through on the floodplains, and often we don't know where the water is coming from, whether it's coming from downstream sources or upstream sources and moving downstream, and usually it's coming from a combination of the two. So our other question that we were addressing is how do we connect low flow events with storm events? And since low flows are generated by gaps between storms, not storms, we need to look at the distribution of gaps, not the magnitude of storms. Although obviously compiled infiltration over time will fill up storage. Evapotranspiration will take water out of storage, and we have to look at all that as well. But taking the simplest thing first, which is how big are the gaps between storm events, Alex Lassner looked at this and said, well, I could come up with a metric for that, which is what he did. And then he used that to evaluate essentially how precipitation was distributed in the United States. You can see that with more gaps, it's going to be in these pink covers. With fewer gaps, it's going to be in these greener colors. And along the East Coast here, you say, oh, it rains all year round. And on the average, it rains here about every 7 days, so we get year-round precipitation. But we can also look at changes in precipitation. So one of the things that we've been observing kind of colloquially is that it seems like the increased intensity of precipitation and gappiness of precipitation, that those have increased in about the last 10 years. So Alex looked at that and compared the first decade of the 21st century from 2000 to 2010, and then from 2010 to 2020, and essentially took the difference of the latter one to the first one. And you can see along the East Coast here that just about at Maryland, there's a shift between decrease in gappiness of precipitation to the north and increase of gappiness in precipitation to the south. So that tends to suggest that we're in this area where we might be seeing either variable gappiness in precipitation or an increase in gappiness precipitation, and it's superimposed on top of whatever is going on in terms of those underlying geomorphic and geological controls. But we haven't addressed the question, does an increase in gaps between storms lead to lower base flow or to maybe the lowest of the stream flow? So the lowest of the stream flow is a metric that is also used as one of our extreme stream flow metrics. We call it the 7-day low flow. That means we average the low 7 days as opposed to instantaneous low flow. And then we do a probability analysis of that. It's just like a flood frequency curve, only your 100-year event would be a really low flow, not a really high flow, okay? And you can see here for the Patuxent River, lots of the time it's just sort of slowly draining out, but then some of those low flows, this is a forested watershed, are really a lot lower than some of the others. So once we have all these records, we can go back and look at the really low flows and try to figure out what's actually going on with them, whether they had bigger gaps in those years and whether they were hotter and drier and whether that was driving flash droughts. We did notice a correlation. We noticed a similarity in pattern, because we haven't done a more detailed analysis of it, between this distribution, this change in gappiness that Alex Lassner observed, which is decrease in gappiness to the north, increase in gappiness to the south, and that corresponded pretty well with a 7-day low flow analysis by Dudley et al. We're seeing an increase in 7-day low flow to the north, as that's the trend, and a decrease to the south here. Okay, so what's the result of this? The result of this is we really have more questions than answers. Another one is, I think, a combination of looking at the morphology, learning what we learned from the northwest branch of the Anacostia, which was nearby and really set up to study, and we could get to it quickly. But it's really giving us guidance as to what's going on in that heavily populated big roadways crossing the stream near the Potomac River, which is also not particularly well gauged and involves a lot of hazards for a lot of people. So these heavily urbanized portion of Maryland typically has small streams, some with shallow bedrock and narrow valleys, and these respond rapidly to these short duration, 1 to 3 hour intense storm, and sometimes even shorter duration if you've got a case like we saw in Greenbelt. We can identify these streams that are at risk and maybe question whether these are the ones that we might want to put some real-time monitoring on it so that the data gets relayed somewhere instantaneously. All the data I've presented to you so far, I just go out and download the data and I analyze it, and my students analyze it. But we're not looking it up and putting it on in real time because most of them aren't creating a hazard. But some of these ones that we've identified are creating hazards. The other thing is we should really think about our patterns of urban development. The pattern of urban development we see pretty much throughout this area is occupying these flat ridge tops, which have this permeable soils and storage space for the infiltrating water that can both mitigate the storm flows and supply the streams with water at low flow. And that's something that we might want to think about. All right, I finished early so I can take times for questions.
Okay, so wave me down if you have any questions. And for our online people, you should just be able to unmute yourself. But if you can't do that, type your question in the chat. Oh, Louis, go ahead.
Karen, it was a really great talk. And what I wonder about is there's another question here that as these streams become more vulnerable to the short-term events, what happens when you do get one of these historic events and like the Agnes flooding? But there's also another type of flood that you didn't mention. And again, another rare thing. 1996, we had 20 to 40 inches of snow over a broad area in 1 week.
And then we got rain on snow.
Rain and fog. It wiped out the entire, and people in southern Pennsylvania and western Maryland compared it to some of the floods they saw during Agnes.
And I didn't even talk about the floods that we see on the Potomac River, which are dominantly spring and winter floods still.
So do these smaller, is there increased vulnerability within these rivers that you're studying to those types of events?
Absolutely. The upper part of that flood frequency curve that I showed for that small 12.5 square kilometer watershed, all the biggest events were actually hurricanes and tropical storms because they have those bands of high intensity on saturated conditions after it's been raining for 24 hours. So those are mixed events that the mixed behaviors in these small watersheds. Yeah.
And the buildings along those areas, I would assume would be more vulnerable. What happens to that? What happens when that tree goes out? You know, in Greenbelt.
Oh, you like that tree?
Yeah.
That was the question that the city of Greenbelt asked me. They said, well, how is this going to be more erosive? And the thing is that the erosion isn't coming from the top down. At the top, it's actually depositing. But if you get a big enough event, it just goes over that waterfall and undercuts it. And it did undercut during the summer storms this past year. But the magnitude of those storms, the intensity of those storms boggled my mind. There were 10 events that were in this past year that were bigger than the 100-year event. Those were 30-minute events. That was frightening, yeah. Which actually brings up another matter, which is we are analyzing a lot of data based on daily precipitation values because it's the most easy to access through DayMed or PRISM or something else. But we really need the shorter duration precipitation records from throughout the state of Maryland, which is what one of the other projects is really obtaining for us. The HydroNet, yeah.
Any other questions?
Have you guys looked at, so there are these like low-cost weather networks that are out there. I own one. I think Mark has one. They're not calibrated, but there's quite a few of them. Have you
Oh,
guys?
we use them.
Okay.
Yeah, anybody who has a network, we go barge in on them, yeah.
Okay.
Yeah, so if you've got one that is in the area that, we're expanding what we're looking at as well. So we're gonna come knocking on more people's doors, I think, yeah.
Yeah, there's ambient weather, there's weather bug.
Yeah.
And it's actually very interesting if you're weather weenie like me to look
Yeah.
at them during these events. It's amazing.
And that's, yeah, we need more fine scale precipitation data. And, we're getting it through the University of Maryland program, but yeah, we need more data.
Okay, all right, thanks.
Questions?
With the gappiness in the storms, have you looked at the soil moisture and how that is affecting the runoff and the quick flow?
We aren't right now, but we are strongly thinking about that as a component of our next project. So what are we doing next? We're doing a bunch of different things. We're checking to see whether the trees actually adapt to the geomorphic and soil conditions that they've dealt and see whether they behave differently. So that's one of the projects we're looking at. And then the soil moisture is obviously another important one. But that gets you monitoring lots of spaces. It's not an integrative measure like stream flow is, yeah.
Karen, thank you so much. This is really interesting. I was wondering, do you have any, have you done any analysis on what type of urban development contributes to the great runoff? I mean, hypothetically, we know, but specifically in
Yeah,
this area.
we make lots of observations that we think we understand that. And I'm also playing around with that. It's sort of coming back is what question do you want answered? So if you're looking at a long, narrow stream channel and saying, okay, we need to mitigate the runoff on the major stream. The fact that some are fast and some are slow, the tributaries of similar sizes, if some pop off quickly and some over a longer period of time, that means they're going to get their flow to the main channel at different times. So that might be a good thing because it spreads out the flow along the main channel. If you're looking at, you're going to erode this channel, it's going to undermine a community, obviously you want to mitigate the peak flows. But you really have to have the right questions to be addressed. And that's something we haven't quite decided yet. Yeah. I think for the Northwest Branch, it really is what dumps in downstream because the flooding downstream, they keep having to raise the levees so that Hyattsville and Bladensburg don't get flooded. So it might be that's that's what needs to be paid the most attention to.
Any other questions in person or online?
We have an online question. Do you have any map data of soil depth to bedrock?
Do I have any what?
Any map data of soil depth to bedrock?
We do, but we don't. We haven't put it in a map that's available to anybody yet. And we also have relationships between the steepness of the hill slopes and the depth to bedrock that could be used to estimate it in other areas. And we need to, we've looked across at other watersheds, because the other thing would be, can the relationships we develop for, let's say, Northwest Branch be used in other ones of these watersheds? And that would be really important to figure out as well. But we think we can maybe come up with functions that could be used for other watersheds.
James Hyde has his hand up. James, you can go ahead.
Hey there, Karen and everybody. Thanks for this awesome meeting. I have some comments related to summer storms and stuff. So for everybody's awareness, one of our undergraduate students, Madison Magaha, looked at the 100-year storm event. Since we have this new high-resolution rainfall data with the Maryland Mesonet, we're measuring every 3 seconds, which is unprecedented, rather than using daily data. And
Or even 5-minute data.
Or even 5-minute data, yeah. And so even with the summer storms, we were getting rain rates that exceeded any sort of thing that Atlas was pointing out. And it's true. Even if you look at the 1-minute data across from airports and stuff, Atlas is underdoing the amount of rain rates by 20 to 50% in some cases.
I agree, yeah.
And so, but we're just now finding that out because we have the data to prove it. And so we're working with both the Atlas team at NOAA and here at CRN to try to figure out what is actually going on with this stuff. And regarding the soil moisture, we're also doing that too. And so we're trying to link all these data sets together.
So how many Mesonet sites do you have that are in kind of the region I was talking about? This kind of heavily populated region is one of the areas where we don't have many Mesonet stations.
Yeah, so the Greenbelt, we have the College Park station. There's another one that was just put in this year at Lay Hill. That's at the headwaters of near the Trolley Museum by 200. The good news is that Montgomery County is partnering with us to install more stations in that region. And so for Rock Creek watershed, there's going to be probably 2, and then for Northwest Acostia, general watershed, there's probably going to be another 2.
And the Cabin John area would be another place that
so the Cabin John branch, there's a new weather station actually went in 3 weeks ago in the Potomac area.
Good.
And so we're just starting to get collection data on that. And all those stations have soil moisture down for it's 2 inches, 4 inches, 8 inches, 20 inches, and 40 inches. So we can really tell how much is being soaked into the soil versus how much is going straight into runoff.
So maybe I should put my next set of gauges close to where you guys are monitoring.
We'll collaborate.
Yeah. Okay. Thank you.
And if you want to learn more about the Maryland Mesonet, James Hyde is our next speaker in a month. So what a nice opportunity to plug that. There was one online question that was a follow-up to the map data of soil depth to bedrock. That was, how do you estimate these depths simply?
Oh, you mean from the seismic surveys?
Yes. And Jin Wang, if that's not what you meant, go ahead and chime in.
Right. So we're doing these kind of putting in, we're monitoring after making a kind of a hammer on a plate and making an acoustic sound that's penetrating at depth, and then it bounces off at depth, seismic reflection. And so we're measuring the time that it takes to come back to us. And that's going to be a function of the depth and how tight the rock is, how fast the wave moves through the rocks. Anyway, it's a lot of processing that Hung does with that. And then we also have soil cores where we dug down to that bedrock soil interface, and we've done that at a bunch of places as well. And in some places, it outcrops in the stream directly.
Thank you. I think we have
All
time
right,
for
thank you.
one last question, if somebody has something burning. Okay. Well, if not, thank you so much to Karin for giving us this
Thank
great
you.
talk. And thanks to everyone else for being here. We got one more seminar of the fall semester. James Hyde kind of gave us a preview. December 10th, same place, same time. Thank you, everybody.